Yeah, so we are here. So, so we prove the existence of the function. I will change the variables, still 6 variables, but I will change the names because I need letter V. So, and this function had the properties that BQ is non-negative, defined in the domain omega q, where there are many conditions, but the main, the most unpleasant condition is non-concave one, non-convex one. Several other restrictions, but they were convex. And there was a differential property of this function. So if you apply it to, so it's in a certain point V, so let's call it V, in the domain, this vector. So at any point V, you consider the second differential form on any vector dV, it's bigger than dV3, dV4, which in my notations is d capital X, d capital Y. So that's what we know exists. So in particular, this condition can be translated. So this is infinitesimal condition. But it can be made sort of global condition. So notations are, of course, V is X, Y, etc. V plus has the same letters with pluses. Y plus has the same letters with minuses. And the geometry is that we have all these points in our domain, which I cannot draw the picture of 6-dimensional domain, so I will draw only this unpleasant piece, projection on the plane xy. And so all these 3 guys should be V plus, V, and V minus should be in the domain. So then we have this property. It follows from the infinitesimal property, but you see it follows immediately, but still not in 1 second, but in 2 seconds. Because if you make, and one more condition that, of course, V is V plus plus V minus over 2. And if you make this straight segment, you see that it can happen that the whole segment lies in our domain. And then, of course, it follows just from an infinitesimal thing. But it very much may happen that it lies out, a piece of it lies outside. So one should be slightly careful here. But you see, if you just use a new notation, for example, you denote by BQ the previous B of 2Q. So then it will follow quite easily because this thing doesn't go too far from omega q. It's easy to see. On the other hand, now I will formulate the lemma where I will need this inequality where I don't have 2 points and the point V, which is the barycenter of this. But when I have as many points as I want, and I still want the same type of lemma. Well, that seems completely impossible because even for 3 points, we can have 3 points all in the domain, and their barycenter also inside the domain, but the convex hull of these points is as far from omega q as possible. And so Seems like we are in some trouble if we want to generalize that. And why we want to generalize that? Because we want to prove A2 conjecture. For A2 conjecture, we need a certain inequality of this type, which I'm going to formulate. So it's a theorem. So let us have V and Vk in our domain omega q, and V is the barycenter and some combinatorial condition on this cloud of points, which I will tell you later if we come to the point where we need to tell this. So then we have the following. So some constant which doesn't depend on n, it's some absolute constant. Actually, it is 1 over 120, and it's yeah, that's it. So there are two difficulties here. So one difficulty I already explained, that convex thing can go outside very much, but you can say maybe you alleviate this difficulty by some secret condition here. Well, in fact, there is another difficulty which I don't alleviate at all by this secret condition. Here is this other difficulties which seems even more serious, and it's a difficulty when n, so this thing is n equals 1. So even if n equals 2, we have second difficulty. So here it is. So we have a barycenter of 4 points. And let me draw them in this picture. So how one wants to prove such an inequality? One wants to prove, of course, starting with this one. So here is the point V. We jump here and here, use this inequality. Then from here we jump here and here, use this inequality. From here we jump here and here, use this inequality, add them up, and we should get something like that. Now let us look what is something like that. It shows, well, here you can, with the price of small constant, you can write it as x minus x plus, because x is the average. And here also, just the difference between minus and pluses. And so here it's sort of discrepancy in y direction times the discrepancy in, excuse me, x. Discrepancy in x direction times discrepancy in y direction. So if your barycenter is like that, so it picks up discrepancy in here times discrepancy in here. Now, if one of the discrepancies is 0, it doesn't pick up anything. So if you go from here, jump here and here, you will have trivial estimate. Your function is bigger than 0. If you jump from here to here, now discrepancy in other direction is 0, and again you will pick up 0. So there will be absolutely no estimate of non-trivial type. So even for n equals 2, one has small difficulty here to prove such inequality. So, so let us leave this lemma for a while on the blackboard, and let me explain how to use it. suppose it's proved. So proof takes some pages. Done. Okay, so how to use it? Now we want to prove A2 conjecture. So T is a Calderon-Zygmunt operator. Doesn't matter what it means, everybody knows. And so we want to prove that this estimate. Okay, so first thing I need to explain that there is a dyadic structure in each Calderon-Zygmunt operator. So there exists a probability space of dyadic lattices such that such T is where I have to explain what are these operators PP star and SN. I'm very much not inclined not to define what is P, but still I will very briefly. So it is L So it's called paraproduct, and it looks like this. You take all elements of your random dyadic lattice, you average, and then you multiply by a certain type of constant, which depends on this L and depends on earth generation of its children. And here it's the normalized, as always in my talk, in L2 Haar function. So it's a paraproduct if it satisfies the following condition. Some So you may ask, what is this constant R here? It will be explained later. It's a certain fixed constant. Okay, so this is paraproduct. And then what is Sn? Well, this is interesting to explain. This is the shift. So this is dyadic shift of order n. And so the typical dyadic shift of order n is the following operator. j. And how we do this with I and j. So we consider, again, dyadic subintervals are children of L, but and also j. And let us have let us be m, m prime, n. So let it be m prime. And I should say something about normalization of these constants. And normalization of these constants should be like that. And here I can make a mistake. Maybe it's L. I think it's L. Yeah, it's L. Okay, so what this operator does, it takes sort of, for each L, we should go through all L's on Earth in this dyadic lattice. It takes the level m energy and throws it to level m prime energy. So this is what it does. And in fact, it's only an example. It's an example of level n dyadic shift, because more generally you can write the dyadic shift as follows. It's the sum of I write it as not the shift itself, but the kernel. It's the sum of operators, or the kernels, which have two properties. So first, AL is less than, say, 1 over L. And second, this operator, this kernel, maps dn L to itself. What is dn L? So take L, consider all functions on L which are constants on the 2 to the nth, I'm sorry, on the 2 to the n generation children. So you divide the interval L to small intervals up to generation n, and consider just step functions which are constants on this. So let me immediately come to here. Which one? Capital L? Here? This one? Here? Yeah, of course it's inside. It's the same lattice, right? Same guys from the same lattice. If it's 0, it's okay. No, it cannot be empty. You just go several generations down, so you have children. Whether I forgot the length of L? No, I think it's already here. No, I don't think it's needed here. I think it's correct. Okay, so let us look at this two. And P star is a P star, right? Yeah. Thank you. simplest is R equals 0 when just L equals L. So let's look at these two blackboards at the same time. So how we will... So the idea, of course, now is clear. The idea now is to prove, if you want this thing to be proved, you need to prove it separately for these dyadic blocks. You need to prove that norm of every para product has a linear estimate, and then you just average, right? It's a probability thing. And you need to prove that the norm of Sn in the weighted space grows slower than exponent in n, because there is a positive epsilon there which will kill the growth. So what was this inequality? This inequality was what actually proved Whitwer inequality. Or actually the other way around. Whitwer inequality proved us this theorem, but they're equivalent. So if you have this theorem, this one on the top, it also gives you Whitwer inequality. Because what you do, you just plug here average of your weight, here you plug average of your inverse weight, here you plug average of one test function, plug average of another test function, here you plug L2 norm weighted of one test function, and here the other test function, L2 norm weighted. And all this enumerated by the interval I. So this averages over I, so you have a function on the tree. You have a function on the tree, and for this function on the tree, you have the estimate of its Laplacian. So using the formula of Stock's formula or Green's formula on the tree, you restore Whitwer inequality. Now, what this means? It means that, again, you have a certain function on the tree. Well, actually, the same function, because you take the same function b, only you change q to 9q, and you plug the same averages everywhere, so you have the same function on the tree. But now you are proving some different inequality. So what kind of inequality you are proving here? So you see, this will be the average over, I don't know, L. And these guys will be the averages of the well, these guys are ancestors. How to say about that? How? No. No, children, yeah. But these are children of nth generation. Huh? Descendants, right. So, and so these guys will be descendants of nth generation. And so, again, we can hope to use some kind of Green's formula, which amounts only to summing up this inequality over all nodes of the tree. But what we will have then on the right? Well, on the right, let's see. We will have average over the L, average over ancestors, all ancestors. So these are values of function which has constant values on all ancestors and have average 0. This is exactly dn. So this looks like we are having here integrating the function from dl, which corresponds to the first step function. And here we are doing the same thing with the second step function. So if we will be able to see that, in fact, this sum somehow corresponds to the action of this operator on test function phi, comma test function psi, then we will prove what we want. So for that, we need to see whether the normalization is correct. For example, here normalization is integral over L, ALXY, phi of x, psi of y. So what kind of normalization we will have here? So normalization is this. So 1 over L will come from AL. And also we have integration. And let us make the general notation for these guys. So each of them will be called J. And so we integrate over all J's, but twice, in X and Y. Okay? So this is a normalization. And if we would have extra 1 over L, then we will look at this thing and see that's J divided by L, another J divided by L. So we have L. J divided by L is 1 over 2n. And another J divided by L is 1 over 2n. And we will just put this, we just identify one of this 1 over 2n with this one, and identify another one with this one. And then we will sort of write that this thing is, you see, it doesn't have this L. So it's 1 over L, this AL xy integral phi c. And if we will start to sum over all L, seems like we are summing over all L's here, and it means that we are estimating this thing from above. And here you see telescopic sum, it will cancel out, everything will be just 0 except the first term. We don't have an infinite sum, we have a trivial estimate. So there are a couple of difficulties. First of all, what to do with this extra L? Something is wrong, seemingly. Well, nothing is wrong. The thing is that we can see it even here on this 0 stage of the proof. So when you write this estimate, put it on the tree, when you put here averages, put it on the tree, and then you sum up. But you should sum up, what does mean Green's formula? Green's formula is a triviality. You just sum up such an equality for each node. But if for the first node you have this, for the second node, you will need to take it with the multiply 1/2 to cancel these guys from the first node, etc. So in reality, we will not be doing such estimates, but we will need to estimate on a certain normalization constant. And it's very easy to see that normalization constant will be exactly the length of the interval if we put here the average over L. And so this guy will cancel out. And what we get? We get that the certain sum, but be careful. If we start here with node I, then we go to nodes I plus and I minus. But if we start here with the node L, we go not to L plus and L minus. We go to descendants of n generation. So if we sum all these guys up, it will be some rare sum over n generations. So it's separating of scales thing. And so here it's not the whole shift. It's a separation of scale shift. But we have only n such separation of scales. So in fact, I think I proved, if we believe this decomposition and if we believe this estimate, I proved that. So theorem, norm Sn, L2W to itself is done. And well, now of course we can sum up this third sum, and we need to do something with first and second, or actually only with the first. For that, I didn't prepare the Bellman function. But there is another guy of, I think, 1, 2, 3, 4, 5 variables, which will deal with, so it will be exactly like this one, like this of 6. So sort of repetition, which will deal with paraproducts. And so we will be done. So now I have to explain two things. This lemma or theorem which I'm erasing, and the composition. The composition is much more beautiful to explain. So maybe I will first explain the decomposition. Lemma is also sort of fun because it's like getting something from nothing, because it's like trick with the convex functions. So the composition is a funny thing. So let me explain it in a certain brief manner. So where does random d-adic lattices come from? First of all, I will immediately give you this probability space, not to make any mystery of this. It's a simple probability space. So let's think that we have a very fine mesh of intervals on the line. And then, so we declare them members of our d-adic lattices. And of course, their ancestors, their descendants is very easy to construct. You just divide each in 2. What's more interesting, how to construct ancestors. So you flip the coin, and if it's +1, you say that this is father. And if it's -1, you say that this is father. As soon as you define one father, you define all fathers. And then independently, you flip the coin again. So if this became your fathers by the previous flip of coin, you again have 2 choices. One is this becomes father, one this becomes father. And so you continue in this manner, and you construct the certain probability space of d-adic lattices. Unfortunately, its bottom thing somewhere very low, it is sort of fixed. It's not probabilistic anymore. Well, you can take some projective limit of this, some idiotic nonsense, or you can think that actually you are working on test functions, and you need only test functions in a certain mesh, and then you can forget about such things. Of course, then it will depend on function, which is not very nice, but for our purpose, it will be the same thing. Okay, so we have these lattices, and then the next thing is a very important definition. What is a good cube? So it's good if the distance from Q to R so it's you fix, yeah, we fix it for any such that so the cube is good. It's maybe more convenient to explain when it is bad. So it is bad if So this Q so there are two things. There is a certain relative distance from Q to R. Relatives, I mean, that you should divide by, say, LR, everything. So everything becomes normalized by LR. And then you compare the normalized distance from Q to R to a certain power of the size of Q. So Q can be still good if it's very close to R, but then its normalized length should be the fourth power of the distance. I said fourth if it's one quarter, but in fact this gamma should depend on the operator, on the depends somehow on Calderon's event operator. So then if you choose R large enough, it's rather easy to see that the probability of the cube to be good, or it may be better to say bad, is less than and so if you choose this C2, if you choose R sufficiently large, you can have it less or equal than 1/2 uniformly for the cubes. Mm-hmm. No, there is no, it's no. And in fact, because everything is completely homogeneous here, the probability to be good or bad is the same for every cube. In fact, one can do it for some cases when there is no homogeneity, like on metric space and things. It's very easy to do that. So you take this inequality, and then you declare some of the good cubes bad. How you do that? You take for each cube independent random variable and independent from omega, and measure the temperature of each cube. And if it has a feathered temperature, you send it to bad guys. So then you can always guarantee that you have the same probability to be bad. Well, it's convenient to have same probability to be bad, because here is the theorem of T linear operator. So the expectation of and here I should write, of course, they're in same dyadic lattice d omega, LQ bigger than LR, and R is good. Is equal to 1/2 expectation of the same sum but you forget about saying that R is good. It's not lemma, it's well, maybe lemma, but it's sort of theorem. It has a beautiful idea behind it. So first of all, notice that this, no, don't notice anything. Notice one maybe important thing, that I can replace here big or equal by bigger. It's a second part of this theorem. So if I take this expectation, it's a random thing, right? If there will be no condition, it will be a sure thing. It will be just TFG. So let us add, this is a triangle sum, let us add another triangle sum with less. For each other triangle sum, I also can write the same equality by the second part of this lemma. So what is so important here is that the smaller is good, right? So then I add this up. These two random sums add up and become the sum over all QRs, becomes non-random. And if I sum them up, I have 1/2 TFG, because it doesn't depend on probability. It's just for every d-adic lattice, however random it is, it's just the sum of all QRs is TFG. But here we have two sums and two expectations, and I will not be adding them because it's useless. What I will be doing, so you see, after that I have a representation of TFG. TFG is equal to a certain integral of all d-adic lattices of some huge sums. And there are two huge sums. One is when R is inside, when R is smaller than Q and R is good. Another is, again, the same structure, smaller is good. Okay? And then I do the following. I look at these sums where smaller is good, and I split them to blocks, very natural way. So how two cubes can be located? Or for example, we have a bigger one by size and a smaller one by size. They can be separated. This is the outer sum. And then we can say how separate they can be. Maybe take a big one and say 10 times big one. That's where the small one lives. And small is good. Or there is an inner sum. So when Q is a bigger one, R is a smaller one by size, but R is also a smaller one by inclusion, so it lies inside. But again, it's good. And the goodness allows us to estimate this matrix coefficients of operators. And it allows us to estimate this matrix coefficients. Let me just write once. So one of these estimates is something like, so R is inside Q, R is good. And so there will be something like that. Here it's volume, but it's also length, right? The thing is that it doesn't matter that it's on the line, it can be anywhere. So then Q and R, Q is different. So this is one of the estimates. Now see what happens here. This is this normalization of the shift. There was some square root. You can say you had R in the denominator. So here, I think Q is smaller. Q is smaller. Q is smaller. So it's from the second sum. So, but you see, if it is exactly what I had. It's if you multiply by square root of R, you have square root of R, square root of Q, and R in the denominator. And in front, you have this exponent which I need. Right? So if LQ is much smaller and descendant smaller, I will get this. So these are coefficients of the shifts, and these are these exponential coefficients which I have here. So this here I should say cheating. This inequality is cheating because there is a second part. And this second part I don't want to write. It will give us P. So inner sum gives us paraproducts. Outer sum, when they don't intersect, doesn't give paraproducts, always sums up to shifts. But in this estimate, I used the goodness. And this is how this epsilon appears. This epsilon and gamma have formula epsilon is gamma over n or something like that. Excuse me? Yeah, here Q is smaller than R. Yeah, it's from the other sum. Yeah, it's from this one. Where Q is good. Okay, so this is how this decomposition works. If only we prove this theorem, which I very solemnly call theorem, because it has idea. Okay, so the main thing is to see that averaging over the places where R is good and R is smaller is exactly 1/2 of the whole triangle thing. Yeah, there is a relation between epsilon, gamma, and RD, with D where we are doing that. So this it shouldn't be necessarily on the line. Anyway, so there is a simple formula between epsilon. So epsilon comes from Calderon-Zygmunt constant, of course, and then gamma you calculate by this epsilon. It should be sufficiently small. Epsilon, where? Here? Epsilon. Yeah, that's this same epsilon, but this is n. N is the order of the shift. So how deep we go, you see LQ divided by LR is 2 to the minus n. So we get exactly 2 to the minus epsilon. Okay, so I want to explain the proof of this. By the way, where this randomness come from? It came from problems related to Vitushkin problem. So there on the plane you get very bad measure and you have to work with L2 not in RD dx, but L2 C with awful mu. And there this random grids were very important because they allowed to kill the non-homogeneity of mu. And here there is a super homogeneity, but it turns out it's again very useful because you can then write such dyadic decomposition. Okay, so here we do the following. We split this sum to the sum of all QRs from the same minus the sum where the larger is good. Larger, in this case Q. And we take expectations for both of them. And do the same here. Now, that the first one equals 1/2 of the second is a triviality. Because what we are doing, we're writing here T F good G expectation. So what is TF good? You just write the hard decomposition of F. It's a sure thing. But you leave only good Qs. It's a random thing. Okay? And here you can put this E inside. And what is the average of F good? You just need to see what is the average if Q is good. But it's the probability of Q is good, it's 1/2. So it jumps out, this 1/2, and we have the whole thing. It's a triviality. Here we want really inequality, real equality. It's otherwise will not really work. So it's, we use the inequality, but then there was a certain error, which is a very small error. But if you would try to do it for A2, for proving A2 conjecture, instead of this estimate, this small error will give you this estimate. And this is Hutenin who took off this logarithm exactly by the idea that you should have equality. Okay, so what you do with this thing? So you don't, here you just don't think about sum. You take individual term, THQHR, FHQGHR, and condition it to the following condition. Q and R lie in the same d-adic lattice, and Q is good. But because Q is larger, its goodness is completely independent of what is R. And it's again 1/2. We're done. So then we sum up over all things. And so this finishes the theorem, then it finishes the composition, then it finishes practically everything except this convexity trick. That's true. So one can of course decompose F and G in separate d-adic lattices, and then our probability space is this independent. And I think that here you need one d-adic lattice, but it was also in one of our papers. So it was one d-adic lattice for both guys, right? It's kind of amazing, but that's true. But it was already, it was in after paper, so one d-adic lattice was used already. One random lattice was used. Now here one basically needs. Will it work with this model? Yeah. You see, you really need, if you decompose this, it's very convenient that one, probably you can, but it's very convenient when you have such an order that one should be inside the other. Or, yeah. But I think one can do it with two also. Okay, so convexity, maybe I will leave for the beginning of the third lecture, the proof of this convexity trick. And then this A2 will be completely finished. Thank you. Yes, this is those guys. It should have this epsilon. It should have it should be like that. Oh, no, it's not convolution type. No. But it should have this. Yeah. Ah, okay. No, no. Convolution has nothing to do with it. Yeah. Yes. A2. Mm-hmm. 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 One can try, but I'm afraid that no. I'm afraid that one needs something. But of course, one can try, but I doubt. You see, everything here boils down to very simple thing, whether you can really estimate this picture well, where they're very well situated with respect to each other, like that or like that. So in principle, it's just a condition on the coefficients, not on the kernel. Yes, yes. Oh, yeah, yeah. So there will be n when you make the estimate. The jumps n, but it sums up by exponents. So. Mm-hmm. Hmm? Uh-huh. Mm. I don't know. Good question. Yeah, yeah. What is the convex hull? I don't know. No, I don't know. Yeah, well, good question.